might have to replay this. It's so good.
Yeah.
I quite like it actually.
How do we have 3 viewers earlier and none now?
They left. Or maybe we were the 3 viewers, just us 2. And lag.
It's got to be the theme tune, doesn't it?
Yeah, I think this should be your theme.
This is the best theme tune.
This was the OG
Yeah.
theme tune. This is the one we played on the launch event.
And we made a GTA themed cover of all the people, all the speakers.
That was so sick.
You know, what Sam said? He was like, oh, maybe like Michelle knows something about voice application.
Why?
Just like she recommended us to keep track of the app.
Perhaps.
Which explains why Julie is signing up today. I'm just gonna laugh so hard when we get a flat out rich.
Hello, anyone who's there? We're just waiting now for everyone else to arrive. And listening to some banging tunes. Yeah, so tonight we're going to teach you optimization without ML from scratch. Oh, that's nice. Little variation on it with the little bell. No, there's a different one.
Is anyone streaming?
Yeah, 2 people.
Yeah, I think I'm on it.
Those little bells are really
That's
nice.
really trippy, guys.
Well, they're infinite.
You're streaming now, by the way.
Two viewers, one of them being
Should be one more theme song. We'll go.
Hello everyone, yes, we're just waiting. We're gonna start in 2 minutes.
Later in the week, we should do like prize giveaways or something. We should think of a way to do that.
the people are coming up.
Huh?
The people are coming back.
Yeah,
True
that's a good idea. We should track.
Waiting mode.
Oh, we should have a loading screen, shouldn't we?
Yeah, we
Make
need a
one.
loading screen, yeah.
That'd be sick.
Yeah, we can't add source image. Everyone, add yourselves on the chat so you can ask questions and stuff like that. Okay, I'm gonna get ready to go now. Alright, so hello everyone. For anyone that's new, I'm Haroon and that is Harry. Are you on screen? Yeah, that's Harry. I'm gonna be teaching you guys. I'm gonna be doing the coding today, and he's gonna be answering questions in the chat. So yeah, I mean it's 9 o'clock. We should just get right on it, I guess.
Yeah, just explain the process about asking questions and.
Yeah. Oh yeah. I mean, if any of you are still new, you can basically use the chat on the right. All you have to do is enter a random username on the right side of the form, press enter, and then you can ask us questions in the chat. You don't have to sign up for anything. So yeah, let's just get started. So today I'm going to be teaching optimization, which is a crucial thing that you need to understand if you want to know how to train machine learning models. So what exactly is optimization? So optimization is when you have an equation, something like, let's say y equals x squared, and you know, usually the functions that we're trying to optimize are way more complex than this, but this is a very simple case just to demonstrate the concept. So we have this function x squared here, and we want to find the minimum value here. We can plot this so we can see it, right? So it's easy for us as a human to just look at where the lowest point is, if we can plot the whole thing. So if we want to actually like do that, we usually don't know what the function looks like. The way this this display is like showing us that plot is it's computing it for each value. Okay, so actually, yeah.
I would want to do this about, like,
Yeah.
it could represent a loss.
So yeah, let me just get into idle so I can. Okay. Okay, I'm just gonna increase this here. 11, 14. Okay. Can everyone see that code?
If that's not visible, just put it in the chat.
Yeah, is that visible for everyone? Yeah, just let us know in the chat if it's not.
Maybe make it a small bit better. Just 2 points.
Yeah. Okay. So yeah, we have this function, and we want to find the minima, and there's multiple reasons we could be wanting to find the minimum of a function. One example you can think of, let's say this function represents, let me just plug my laptop in. Let's say this function represents the cost of a machine learning model at different points.
What's the cost?
And the cost is a measure of how bad your model is doing. So ideally, if you want to find the best model, you need to find the parameter value which minimizes the cost, which is how bad it is. Okay. So another kind of problem you can think of it is, let's say I have a routing problem, like I need to get multiple cars to multiple destinations at different times. I could represent that as an equation, and then so I could find basically the amount of time that it takes as a function of, let's say, the number of drivers that I have, and then I could basically plot that and find how many drivers I need to for example, to minimize the cost per driver and stuff like that. Let me know if that doesn't make sense. Just put it in the chat. Okay, so let's just get right on it. Lib dot pyplot as plt. And actually, for those of you who haven't set up Python yet, just search onto Google, just search Google Colab.
Show that.
Yeah, Harry, just put a link to it in the chat. Okay, there's a link to it in the chat. Yeah, you just go onto here, you click New Notebook, and you can type code into here. Alright. So, I'm going to be covering 3 different methods of optimization today, and also variations on one of them. So we're going to be doing grid search, random search, and we're going to be doing gradient descent. Okay, so when we're optimizing, we need a function to optimize, right? And we could actually, I mean, let's start with doing x squared. Okay, so let's do x minus 3 plus 4. I'll look something like that. So the value would be, the minimum for that would be at 3. Okay, so first off we have our function which we can plot. X equals np dot arrange, let's say minus 10 to 10. So that's basically going to make an array which goes from minus 10 to 10 in steps of 1. And now we're going to calculate our out value. So that's our x, and we're going to do our y now, which is x to the power of 2. Now I can do plt dot figure plt dot plot y plt dot show. Okay, I'm just going to save this somewhere on my desktop. Okay, that's a bit weird. That's not the x squared function.
Plot x against y.
Oh yeah, true. What am I doing? No, still. Okay, so print y. What I think it might be doing is potentially doing like a dot product or
Y
something.
star 2.
Oh yeah, yeah. Is it? So what does that do then?
Not sure. Let me look it up.
Actually, I've never. Okay, yeah. Harry's going to look up. So I messed up there. I wrote that to the power of instead of star star. Okay, so that's what our function looks like. So now what we can do is just basically check the value at different points. Okay, so what we want to do is test the value of y for different values of x and find the minima. Okay, so here we've got, so if I print x, print y. So if we want to find the minimum of x squared, what we've done here is actually we've got 20 different values, which is basically like 20 values along this line, and we've outputted their y value, and from this we can see that 3 is actually the minimum number. So if we want to find the value of x for which y is the minimum, then we simply do, what we need to do is find the so we need to find the index at which y is the minimum, right? So what we do, if I go to Google, numpy min, so it just tells me okay, that tells me the minimum, but I need the argument of the minimum. Okay, so I can reference it back to which x, because our values for x go between -10 and 10. So if we need to get the value out at the right index. Does that make sense?
Yeah, explain arg, min, and min together.
Yeah. I mean, I think it will make more sense once I just output it.
So the min is the minimum value, and the arg min is the value which gives the minimum value.
Yeah. Okay, so
I don't know if people can hear me on camera.
I don't think so. So yeah, so argmin basically just returns us the index of the minimum value. So what we do is the argmin of y. Print that. Oh.
Harun, do you want to put your editor on the left so that when the screen pops up you can still see everything?
Okay, yeah.
You should use PyCharm Pro.
Print x. Okay. So we can see our 10x values and we see our 10y values. So this number 10 is basically the 10th index counting from 0 of the lowest number in our y array. And that lowest number is 0. So if we want to get the value of x at which that 0 occurs, then we need to index the 10th value of this x array. Okay, so we do min int, so the index of the minimum is equal to that, and then so min x is equal to y of min int. So if we print min x, so it occurs at 0, and that's correct. Okay, so now let's change this so that it doesn't occur at 0, and we'll see if our function still works. So we did x minus 3 plus 4.
Maybe like in the print statements, print like string explanation of what they are, like minimum value, minimum argument that gives minimum value.
Yeah, index of minimum value of y. Index of minimum value of x. And it might not seem like we're doing anything important now, but like getting this foundation will help you understand ML, because a lot of people learn ML and optimization at the same time because they're tied in. What we're trying to do is teach them separately. Okay, so x, so here that was my error there, so it should be x, that's the min x, and we can also get the min y is equal to y of min int. So we can say lowest y of min y occurs at lowest value y value of 4, right, occurs at x equals 3. So if we look at x equals 3, then that is the minimum, which is y equals 4. Okay, so we're doing a really simple function here, right? I'm going to look for slightly more advanced functions just to show you. So that seems really simple, but it won't always work. We need to the reason this works is just because we happen to land on the minima there, right? Yeah, yeah. If you search simple functions for optimization, right, and then you click there. So here you can look at some functions that are interesting that we could try and find the minima of. So let's look at, and different methods will work better in different kind of landscapes. So this is a good function that we can try and optimize, let's say. So that's sine of 10 pi x. Sorry? It's a good one, right? Has anyone asked any questions yet? Np dot sine of np dot pi over 2 times x plus x minus 1 to the power of 4. Okay? So let us lowest of none occur. Yeah, I think this function is only valid for above 0, so we'll have to go from is it valid at 0?
That's indeterminate.
Yeah?
Because it's over 2 hours.
Okay.
I wouldn't know.
Yeah, so 0.001. Wait, so now I'd have to do np.linspace.
Yeah, do np dot linspace from 1 to 10 or something.
No, because it still has low values there. And steps are
What does linspace do?
it's too big. We'll do it between that and 2.5. Okay, interesting. So we can see that's how the function looks. If we increase this, it's smooth. It basically comes out a lot smoother, right? So a lot of the time with functions we don't know what they actually look like, because if we could plot the whole thing, like to actually plot it, we need to compute the values for it. So if we could compute the values for all at every point in order to plot it, then we could just take the minimum of that, right? So we actually usually don't know what it looks like. So
if it were an image, it would have an intractable amount of points to plot.
when we're working with high dimensional data like images, when we're doing some more machine learning, there's too many parameters, like, so
An image can have a million features.
yeah, exactly. Basically, it's there's a name for the problem, right? The curse of dimensionality, which is that the number of points you need in order to sample a space at the same density grows exponentially with each dimension you add.
So if you have a million features,
Yeah, so if you have 1 million features, then that's a lot. Okay, so I'm not going to plot that, because we theoretically, actually I will plot it, and I'll plot our minima on it so we can see what it looks like, what our guess is for the minima. So I'll do 400 there. Okay, so it does find the minima there, right? So search. So what I'm gonna do, okay, yeah. So oh no, okay. Wait, plot. Just give me 1 sec. X equals np dot arrange 10. Okay, so I'll show you what we're doing now. So what usually we don't have this function here. I'm just computing it because this is a small function, so we can't compute all the values and visually see what it looks like. We wouldn't usually be able to do that, right? So what I'm going to do is I'm going to plot it, but I'm going to search that space using a grid search, searching at every at intervals of 1 from 0 to 10. Actually, let's do from 0 to 3. Okay, so, and we'll see what our function, what the computed minima is. Okay, lowest. Oh wait, yeah.
What's the error there?
It's just that I need to do the Y plot. Let's go plot. Okay. So what we've done is we've searched from starting at 1, so we've up to, so we've checked 1 and 2. Okay, that was our grid search because we can't evaluate this at 0. Actually, let me do. So what I'm going to do now is I'm going to decrease the step size. So we're doing basically a more refined search. Now, instead of searching at every at every 1, we're going to search every half, at intervals of a half. And we can see our estimate for the minima didn't change, right? We say it still occurs at at 1.0. The true minima is actually down here. So this got it wrong, right? But we can basically increase how much of a refined search we're doing. So if I do 0.1, okay, so now it's slightly updated it to 0.99999. If we change it again, even more refined search. Oh wait, I know what the problem is. It's because I'm so now we see that I actually changed the estimate for the minima once we changed how refined our search is. So if we go back to, let's say, 0.1, it's going to guess here. It's going to guess 0.9.
Make sure you explain what the errors are.
Yeah. Is everything making sense though? Does anyone have questions yet? Any questions?
Everything is clear. Yes.
Okay, cool. Alright, so that's grid search. So grid search is when we search at along the axis at equal intervals. Okay? Pretty simple. So now random search. Random search is basically the same thing, but you don't do it at equal intervals. You do it randomly. Okay, so index and minimum value. I'll show you how similar actually grid search and random search are, because I'm basically going to reuse almost all of the same code. I'm just going to go up here. Random. So what I need is random numbers dot rand, and this basically generates random numbers between 0 and 1. So what I'm going to do is times that by 10, so it's between, by 3, so it's between 0 and 3. And the number of, basically how many random spots do we want to check? Let's say 100. And then our y, I mean, you can see actually how similar these two pieces of code are, because all I have to do is change one line and I go from grid search to random search. So random search, okay, it checks at random points. What I'll do is I'll plot it. Okay. So this shows all the random points that we're checking. There's quite a few. So let's do only for 10. We'll see how good it gets. So it checked these points. Okay. So yeah, it randomly checks these points and it found out of all these points that this was the minimum. Okay, so if we keep running this, it will basically get us a different result every time. Whereas if we go back to grid search, that search is, as you can see, evenly spaced throughout the whole thing, and it can easily, you know, jump over minima like it did there. Okay. Any questions about grid search or random search before we move on? Okay. So now we're going to do gradient descent. Okay, so now we are going to go back to our old example. Okay, so we're now going to go back to optimizing the x squared function. To the power of 2. So -3. Okay, I'm going to copy that across. Okay, this is the function we're trying to optimize again. So what is the idea behind gradient descent? Okay, so gradient descent is a simple analogy is imagine you're on a mountain, but you're blind, so you can't see around you what's happening. What you can do though is you can take a step in every direction, or just basically like take a step in each direction and see which direction that you went in took you the lowest, and then you can just follow that direction to take you to the bottom of the mountain, for example. So that's essentially the idea behind gradient descent. At every time step, we basically look at where we're currently standing, right? We can feel the ground and we can say, oh, it's sloping in a certain direction, and then we can just follow that to the bottom. Yeah, and that's as simple as that, really. So how do we do it, right? So first off, we have this curve here, right? What we do is we start somewhere random on this curve, like here, x squared curve. Let me plot it actually. I don't know why I'm showing it in the air. Okay, so we'll start off. Let me plot that even longer. 20. So let's say, you know, we'll start off here or anywhere along there, and then we just check, okay, which direction is going down, and then we just keep following that until we get to the bottom of our minima, right? Very simple. Okay, so how do we do it? So first we need to start somewhere random on the mountain. So I'm going to say current x is equal to np.random.randint between minus 10 and 10, let's say. Okay, so I'll do current y as well is equal to okay, so that's our current plt.scatter current x. So what I'm going to do now is just plot our current randomly, you know, random position on there. So we random initialize there, right? So now what we need to do is find the gradient. Okay, so how do we do that? Well, quite simple actually, because the function that we're trying to optimize here is x. Okay, so let's do I can do this in my head, but I just want to show it just so it's clearly visible.
Yeah.
X minus 3 power of 2 plus 4. Okay, so I've just put our equation there, right? Oh, here we go. That equation, yeah, it's quite simple to take the derivative of it, right? Like, you guys have done like simple maths. You just bring the power down, comes 2x. Well, 2x, yeah. Let's see. Yeah, 2 times x minus 3. Okay, so that's our derivative. So what I'm going to say, current deriv is equal to 2 times current x minus 3. Okay. So what this is actually there's a small mistake, something I said earlier, which is that the gradient, the gradient thing that we're calculating is, it doesn't tell us the direction to of going down. The gradient mathematically means like when you calculate the gradient, it tells you the direction of steepest ascent. Okay, so the direction in which the function is increasing the most. So what we want to do is we want to go in the opposite direction of that, because if the derivative is pointing upwards that way, then we want to go like in that direction there. We want to go to the right, not to the left, right? So what we do is current x is equal to current x is equal to current x minus and we're going to need to set something here. This will become more clear in a second. I'm going to call it learning rate is equal to, let's say, 0.1. This will make more sense in a second. Current deriv, right? So we want to go the opposite direction of the derivative, but we also want to scale it by a factor of learning rate, so we can control basically the size of the steps that we're taking. So if I do that, Okay. Okay. So what I'll do. Okay. Yeah. So I'm going to show here. Okay. Is the red point is where we started, and the green point is where we ended up after we took the step. And as you can see, by multiplying it by 1, okay, we set our learning rate to 1, and we can see we went way too much that way, right? So what we need to do is scale that down. Now we started here and we took a step proportion like 0.1 multiplied by the derivative, right? So we started in the red and we went slightly closer, as you can see, to the bottom. What I'm going to do now is I'm going to do this in a for loop, and it will like plot the points as we keep on. So now we just did one update. We'd want to keep doing that over and over until we reach the minima. So let's do for I and then range steps is equal to. So this is basically saying how many gradient updates do we want to do. How many steps do we want to take in total. I'm going to say 10 for now. So the current x. So we only need that at the start to initialize, where we are, and then after that we keep on following the gradient, as you can see here. Okay. So current. Okay, so now okay. Okay, that's a bit weird. I was showing that. Oh. Okay, I'm just okay. Yeah, so now we can see we start here and we basically take steps slowly as we reach gradient, and you can see that the step size reduces as we reach the minima. Then the reason is because the derivative basically tells you the slope, and at that point the slope is basically almost 0, so our step sizes will be smaller anyway as a result of that, right? Okay, so that's gradient descent for this particular case, right? Now let's try it with a more complex function, such as the function that we had here. Okay. I'm gonna say def my function, and it takes an x, and it will return return. Let me know if you guys have any questions, by the way. Like, literally any question, if anything isn't making sense. Okay, cool. Alright. So, define my function of x. Okay. So, now, let's do x plot is equal to my function of x plot. Okay. So now it didn't work there because the derivative that we have here is for our previous function, not this new function. So what we need to do is calculate the derivative of this new function. Okay, that is a long derivative. So what I'm going to do is use the same function, and I'm going to put a flag in there. So if they put deriv in as a parameter, we'll return them derivative of the function, not the function itself. So if deriv else so what is the derivative? That's the derivative of it. Okay, cool. We're gonna have to write that out. So it's quite similar to this actually, some of the terms. And p dot sine of 10 times pi times x over 2 times x to the power of 2 now. Okay. It's also a negative. Okay, yeah, I'm just basically copying this equation into NumPy format so we can actually use it in our program. P dot pi times np dot cos of 10 times np dot pi times x all over x. Okay, I think that should be legit. So I do my function of current x deriv equals true. Okay, I think there might be oh yeah, this function is only valid between 0 and 2.5. So what that means is that we need to initialize ourselves between 0 and 2.5. So I'm going to say dot ran 0 2.5 And okay, flow account. So this is gonna get us a random number between okay, so that's going to return us a random number between like 0.001 and 2.5. Oh, here, current y, that's why it's wrong. Current y should be equal to my function of x. Okay. Invalid value counted in cos. So that's in the derivative. Okay. 10 times np dot pi. Okay, what is going on? Yeah. Invalid value. So I'm just going to print. Oh, okay, I see what's going on. So what it's doing is our learning rate is too high, so it's taking a step and it's taking us outside of the 0 and 2.5 range. So hence, yeah, like it's breaking our algorithm. So let's take a much smaller step size. Okay, yeah, okay, that's much better. So we can see now our algorithm started here, and I'm assuming it overstepped. It took a step size too big, like it should have kind of dipped into there, but it took a step size too big, then dipped into there, took a step size too big again. So what we'll do is keep it there, 0.001. And now, yeah, if we started there, it will descend into there. If it starts over here, it will descend into that minima. And here, it's basically highlighting another problem, right? Which is the fact that, you know, every method has its drawbacks and its advantages, right? And this one of the drawbacks is that you can get stuck in. I mean, this is basically every optimization algorithm has this problem. Is that you can get stuck in local optima here. So by following the gradient, it's going to go to here instead of it's not going to go up this hill, right? Because it's following the mountain down. So what you might do, you know, if you're following the mountain, is get stuck in a little valley. Okay. So now, okay, this is. I mean, before we move on quickly, does anyone have any questions? Yeah. Excellent. Okay. So now, you know, we have this function here, right? And we have okay. So what I'm going to do is I'm going to show you another way of doing gradient descent. And this way is basically it's called like manual gradient descent. This is one where, let's say you have some function where you don't have an equation to model it, hence you can't take the derivative of it. Let's say, for example, I am, I've got a factory, and I've got a certain number of people working on the assembly line, right? And I need to optimize that for like maximum throughput, or something like that. I don't know the equation that let's say, I don't know how, like, based on how I could measure that statistically, but I don't know. Let's just say I don't have an equation which relates the number of workers I have to my productivity, or like something like that. And we want to basically optimize that. When we're doing productivity, we're doing like we're basically finding the maxima instead of the minima. It's the same problem, right? You could just basically do a negative, and it becomes a minimization problem instead of a maximization one. So in a workers example, I would basically try and minimize negative productivity. Right? Simple as that. Okay. So what I'm gonna do with known, and actually there are some functions which actually, like, we don't know how to differentiate, right? So how would you go about optimizing those? And I'll show you now. So what we have now is we don't have, okay, so now let's say, in this case we actually do know the equation, right? We need to have an equation so we can plot it and see it. But let's say pretend we don't know this equation, so we can only kind of like sample from it. So I can basically like add a worker here or there, and I can see how my productivity changes, and then I can try and use that to optimize it. So instead here, it's on like, generally speaking, it's the same thing. The only difference is that we calculate our derivative manually. So here we don't have the thing, right? We can't set deriv equals true and calculate it there, so we have to calculate it another way. And the way, like, it is done, well, like, what is the definition of the gradient, like, of a derivative? All it is, it's the difference in y over the difference in x. So all we can do is take a small step in x, see how our y changes, and then divide the two to get a gradient, and then we can just use that gradient. Okay, so what I'm going to do is I'm going to say test x is equal to current x plus let's say plus, just a small step, right? 0.001. You could even say 0001. Alright, and then my test y would then be my function of my test x, right? So I'm going to see for this small change in x, how does my y change? Okay, and then what I'm going to do is my current y, so the y that I calculated, my test y, so I'll say actually, deriv is equal to the change in y, which is test y minus current y, divided by the change in x, which we could put as test x minus current x, but we know the difference there, right? Because we manually set it. We could even set that as a hyperparameter actually, epsilon. And the smaller our epsilon, actually, the better our gradient estimate. So I'll put it as a hyperparameter, and we can play with it and see how well it works. Okay, so deriv equals that, and yeah, it's basically the same thing. Current deriv. Oh right, so I forgot to call this current. in double scalars. Test my notes, come on. Well, double scalars. That was a bracketing issue there. So we can see now, again, it works in the same way. It starts at the top of that hill and it follows its way down. But now we could do this for any function that we wanted. Kind of like, it's even for a function that we didn't know, but we could kind of change the x and measure a y. We can just keep on doing that and yeah, and figure it out. Okay, I mean that I'll call it there actually. If you have any questions, like, well, I can do like a bit of a Q&A part here now. So yeah, I mean, one other thing I can show you is gradient descent, but with momentum. It's a really simple change to do. So I'm going to copy this. Right, and so I'm just going to Google gradient descent momentum. Right, and it's going to show us the equations. So now what we have, instead, like here we were just taking a step. Now it's more like the direction that we're going in has momentum. So it's so yeah, it basically helps us get out of local minima and get over to the next peak. So what we can do here, what we'll need is a current momentum, and that will start out at 0. Okay, and then what we'll do is our new x is current and Almo. So what is this value here called? Beta. Okay. Okay, yeah, so we're doing, so what we need to have is like a momentum decay. That can be a hyperparameter. Let's set that to 0.9. Right, and then added to 0.1 times see. Find the index of each point in our sequence X. Yeah, like while I'm doing this, you guys like write some questions in, and I can answer them quickly before we end the broadcast. Okay, cool, yeah. So now we do 0.1 times we'll do our learning rate multiplied by the current. Okay, yeah, so what we're doing, instead of updating our x directly using the derivative, we're updating our momentum using the derivative, and then updating our x using the momentum. So what that means is that, like, rather than just going in the direction of the current derivative, we're basically going in the direction of our like a weighted average of all of our previous derivatives instead. Okay, so current x minus current momentum. Okay, if I plot that.
Process all of that as well, which is a problem, and I managed to
4.9.
simplify that code, so then I managed to do this thing like
My mistake there. It should be 0.9 times our previous one. And this is so it, like, our momentum is decaying, alright? There's some damping. This is basically emulating friction. So we can see here, it's rolling over these hills, so that suggests to me, you know, our momentum may be too high because it's missing out on these minima. So maybe we should have a higher decay. So here you see, that's really interesting. It came up down here. It like checked up around there as well, but then it rolled back down here. So it kind of, like a ball, it was settled into that minima. Okay, yeah. So that's it for the stream, guys. Thank you for watching, and so as you guys know, I'll basically give you a quick peek into what we're teaching over the current week. We're going to be going into models, loss functions, neural networks, and then the paid event will be front end for creating data sets. You can view them all if you go to the Hacker Hustle website. If you go to the month of ML, you can see everything that we've got signed up. You guys know how to use this. You just put your email here, and then you click to register interest. And then for the ones that have already happened, you can click and it'll show you the previous data.
Explain what one of those are.
Yeah. So what these days are, basically the Saturdays. Every Saturday, it's Saturdays, right?
Yeah, we'll put them in different colour. So.
Yeah, it'll be in different colour, but pretty much every Saturday, it's going to be a paid event, and the reason is because this is going to be focused around deploying. So these are going to be like 3 hours plus sessions where we're going to, you know, like if you have an idea, we're going to build it alongside you whilst teaching you how to do it yourself. And yeah, this is basically going to be geared around like getting an actual web app, like building a web app from scratch, which can deploy machine learning in the back end. And all the other 6 days, they're free. So yeah, tell your friends to come along, share it. Yeah, if you find this useful, let us know. If you don't, also let us know, and let us know why. Like, the chat is really easy to use. Or like, you don't even need to like sign up for anything. Just create your username there, and you can start writing in the chat, like giving us feedback.
It's anonymous as well.
Yeah, and it's anonymous. So we're not going to hunt you down if you give us bad feedback. Other than that, yeah, this has been this has been day 2 of the Hacker Hustle month of ML. Come again tomorrow. So yeah, thanks.
Outro GTA.
Yeah, I'll play an outro song. We can just chill here for.
If there's any questions, just throw them in the
chat. Yeah, we'll be here for a couple minutes just for questions. So.
Yeah. Thank you for asking questions on the chat. Thank you for attending.
Yeah,
and
shout
we'll see you tomorrow
to Max55.
Yeah.
Defcon 1. for asking questions.
And yeah, we'll be here tomorrow for models, right? It's a session on models.
Yes, so tomorrow we're going to be teaching different models. We're going to be going theory and implementation, just as we did today. And all this code is going to be available, so you can use it yourself, study it, show it off, pretend like you wrote it at your next job, whatever.
Nice work, man.
Yeah, that's one. How do you think that went?
That was good.
Yeah, was it clear? I think it was a bit. Yeah.
I feel like maybe we should get some like diagrams and stuff.
Yeah,
like,
I
prepared
think so too.
to just because it makes it easy to explain things. I'll put some visualizations in the chat though.
Yeah, nice. That's a good method of doing that shit.
Yeah, especially when they're interactive, people can play on it too. We should do something like a special prize for the last 5 people every time. It's like the clapping game where you go to the last one.
That'll be sick. Fun,
Yes,
dude.
Peace out. Peace out from the hacker.
Yeah,
Hustle.
peace out for them hacker hustle. Keep hustling, keep hacking.